Hi, everyone. Welcome to our session. Good evening. Today, we would walk through the design and implementation of a self-service elastic analytics platform. We would go over lessons learned and pitfalls encountered while supporting Apache Spark in Kubernetes at Apple scale. We are Zhou and Aaruna from the team that provides a managed Spark service within Apple. With that, let me give a brief intro to our organization and the various services that we provide. Apple, as you know, manages a wide range of services like Apple TV+, Apple Music, Maps, manufacturing, and business insights that need data processing. Our data platform provides frameworks and services empowering our customers across Apple to build business-critical data-powered products, define new data lifecycles, and create their own specialized platforms. It enables our users to leverage the foundational components and expertise so that they can focus on delivering business value. The interactive data science environment is built on a Jupyter Notebooks foundation and is further expanded by our console user interface. Elastic multi-tenant data processing and analytics are built on Spark, Flink, and Airflow. Our high-performance data lake is powered by Iceberg and a distributed ad hoc Trino query engine. A unified metadata catalog forms the foundation of our data governance, ensuring data is secure, accurate, available, and usable. With this context, let us dive into the Spark service within our platform. At Apple, we started our analytics journey using various distributed processing frameworks like Hadoop and Spark on Yarn. This worked well to begin with. However, as the scale of our use cases grew, it made sense to decouple compute and storage. Thus began our journey to disaggregate compute and storage in order to scale them independently of the other. As you can see here, the various jobs can independently scale in the analytics nodes on Kubernetes and connect to the data sources or sinks like HDFS, Cassandra, Kafka, which can scale on their own. Next, let's talk about a typical application lifecycle and dig into a few foundational principles of our platform. A Spark job starts with code. It could be in your Git repository or in your notebook, like in Jupyter. It needs to be built, tested, and packaged into a runnable, which could be a Docker image or a tarball, published to a repository. At runtime, data platform, and in particular, Spark Orchestrator, builds the detailed spec and passes it to the underlying compute substrate. This includes details like the right dependency versions, integration with various secret management solutions, and setting up logging and telemetry support for performance analysis. Next, let's dive into a few core security principles. Security is a top concern for design. When we start a Spark application or a pod, we have application certificates that are injected and provisioned in each container to uniquely identify the workload that is being launched there. It also has predefined configurable network policies for connectivity. Thus, each Spark driver or executor is enabled to connect to a limited set of sources and sinks within or external to the cluster. Encryption. We enable on-the-wire encryption that is transparent to the Spark application. With respect to secrets, in addition to Kubernetes secrets, which as you may know, may be mounted as environment variables or as files, we also support out-of-the-box integrations with various other secret management solutions used within Apple. Next, let's go over monitoring. Users get default integration with logging systems that we use within Apple. And in addition to that, they also get integration with telemetry systems. By default, Spark's metrics are pushed to this telemetry system. In addition, though, users can define other key metrics that they publish from their jobs. And then the users can monitor these key metrics and also set alerts on them based on trend or threshold. With these goals and background in mind, let us dive into a high-level design of our platform. When we initially launched the platform a couple of years ago, our primary integration was with Mesos compute substrate. Let's review the design at a high level. Users can use either APIs or UI or other workflow engines like Airflow to perform various Spark application-related operations, like running a job. As an example, let's pick the run a job scenario. The Spark orchestrator, upon receiving the run job request, would request Mesos to create a driver task. Once the driver task is running, Spark orchestrator, which is monitoring it, would then request the executors, which would connect to the driver and run the job. Next, let's dig into a high-level design using Kubernetes. Picking the same example again of running a Spark job, Spark orchestrator, upon receiving the run job request, would interact with the Kubernetes API server to create a custom resource of type Spark job in the user's Kubernetes namespace, and then create the Spark driver pod and executor pods when needed. Spark operator, which is running in each of these Kubernetes clusters, would also manage the garbage collection of the various Kubernetes resources, like pods, when the job is completed. Also, it would also manage the restarts as per the restart policy configured by the users. With this, let us go over a few numbers to give you all a peek of the scale at which our platform operates. This graph shows the number of Spark jobs and executors that are launched daily. As you can see here, we now launch nearly 400,000 jobs that have around 5 million executors in total. Now, let me hand over to Zhou, who would go over lessons learned and pitfalls encountered for supporting Apache Spark in Kubernetes at Apple scale. Over to you, Zhou.
Thanks, Aaruna. Hi, everyone. My name is Zhou. In the second half, we'll discuss the challenges and pitfalls we encountered while scaling up Spark on Kubernetes, and the common tips that we would like to share to make data platform, as well as the Spark orchestration system to survive at scale. We will start with the challenges that we encountered. As a data platform that serves many teams, there are multiple types of workload patterns that we're going to support. Some of our customers, especially when running batch jobs, would like to design their job in a wide way. Means that they're going to need to schedule up to 5,000 to 10,000 Spark applications simultaneously at the peak time. We call that a wide case. Although each individual application may require only a number, like just a handful of executors, it challenges the orchestration system because the jobs are actually being scheduled at a high parallelism. And since these applications could be short-lived, it is potentially pod churn at cluster level. And on the contrary, some of our customers would like to design their workloads in a deep pattern. There will be a couple of Spark applications, but they may require several thousands of executors and do heavy I/O and shuffle on external file storage. On the other hand, as a data platform, you would always expect both wide and deep case. Means that the requirement to continuously schedule several thousands of Spark applications of average size. And this is kind of like an average load of the data platform across different available zones. The workload may be fluctuating within a day or a week. It's hard to predict like when is the peak time will come. And for some of our customers, batch scheduling or gun scheduling is a hard requirement to have their machine learning jobs running healthy. We evaluate the migration of the workloads from Mesos to Kubernetes. And the initial load test simulates both the wide, deep, and wide and deep cases. It brings down the cluster pretty quick. The etcd storage, which serves Kubernetes cluster, was fully filled within 10 minutes, although it's already is configured as the 8 gigabits, which is the industrial recommended maximal storage for etcd. Why so? The storage actually serves all the Kubernetes resources, including Spark applications, pods, services, as well as the events which are automatically generated when you create or update something in that cluster. In addition, each update to existing resource is actually creating a new version for the original. Plus the pod churn at the hyperparallelism wide case, all this adding together creates significant pressure on the cluster at peak time. As a data platform and Spark orchestration service, another challenge for us is to give a unified interface for all compute substrates, the requirement for bring your own cluster. In addition to the on-prem shared infrastructure, user may come to us with existing cluster and resources and expect to use them and still enjoy the features, the convenience, the security and monitoring features for managed Spark. These are in fact requirements to automatically fast installation of Spark control plane, which typically could include a lot of trivial tasks and human effort for doing that. In addition, unlike the shared on-prem, the bring your own cluster may have customizations and from different cloud providers. And they're going to need access control to make sure that only the correct person and team could use this cluster as a compute capacity. Next, we'll step into the strategies for these challenges. Our on-prem Kubernetes clusters are fully optimized with Spark requirements, including the etcd storage size increased to about 8 gigabits. The store is also configured with more aggressive compaction strategy to survive the multiple updates to existing resources, and also to use separate store for automatically generated events versus other resources like pods, which are explicitly created and updated. Besides etcd, from the cluster capacity perspective, there are also several tips to be kept in mind while you have the cluster autoscaler enabled. While scaling up, there is the trade-off between latency and cost, like keeping a bunch of low-priority pods running as a buffer, and the fault tolerance while scaling down. Namely, the Spark driver pods are not safe to evict from the cluster autoscaler perspective, so that they can survive even if there is potential executor lost. Another critical configuration is priority class. Defining proper priority class in your cluster helps it to understand the importance of your workload. And setting up Spark driver at a higher priority would help to avoid unnecessary crash. Or consider to use non-preempting priority class if you're on Kubernetes 1.24 or above that specify the importance of your workload without preempting the existing ones. IP exhaustion is also a critical issue that may occur when you have hyperparallelism. In practice, it is not uncommon that the new pod creation is much more faster than IP deallocation. And after V4 exhaustion, new pod create would fail because they cannot get IP allocated. This could be mitigated by configuring faster garbage collection, like shorter TTL at kubelet, as well as exploring cluster routable instead of global routable IP, so that as long as you don't expect direct incoming traffic from out of the cluster into Spark executor pods, they are safe to be cluster routable. And IPv4 upgrade, we're enabling IPv6 upgrade, we're enabling v6 for our prod customers for their JVM applications for Spark 248, 3, and above. Besides tuning the cluster, the orchestration system itself also has several strategies to survive at scale. We're going to start with the concurrency control. In the community, in open source connector, the concurrency policy could be defined as allow or forbade or replace, You could just disallow a concurrent run of the same application, or replace the old one with the new one, or just configure it to run at every 5 minutes, even if the previous one is still running. This concurrency control could actually be performed by the orchestration system to make sure that parallelism could be enforced at global level for each individual application or for a given schedule, making it configurable for users and therefore more preferable for users other than just the simple rate limiting. Let's see an example here. The CMO describes that this application, the total maximal parallelism allowed is 100. At any time, there won't be above this number of active runs of the same application at any level. And user may also configure that allow at maximal of 10 concurrent ad hoc manual way of kicking off this application, as well as maximal of 5 concurrent runs from the trigger named hourly job. This concurrency is actually enforced by Spark Orchestrator before scheduling the workload. It gathered the basic information about the application, including its name, the trigger name, Spark version, etc., putting them into an active job run index. And the actual workload will be scheduled only if the maximal allowed parallelism is not exceeded. And the active index will be removed only after the application has completed and relinquished all the claimed resources. Next, when the cluster is under pressure, an unfavorable scenario is partially running due to resource contention. For example, in this case, application A and B both acquired a fraction of executors, but actually they both need 100% of capacity in order to do the analytics job. And this partially running is actually hanging because they're waiting for someone else to complete first and then give back the resources for them to proceed, resulting into a kind of resource deadlock. In order to resolve this, batch scheduler or gun scheduling is the solution that ensures Spark application will be scheduled only if there is sufficient resource for this application. And there are multiple solutions within the community. Spark team at Apple is also actively contributing back to the community to make Spark natively compatible with multiple batch scheduling solutions. But in reality, this scenario may be more complicated because the requirement for bringing your own cluster, the different clusters from multi-providers could have different preferences for batch scheduling. Therefore, the orchestration side timeout kicks in to help with this case. The orchestration system will identify the applications that are hanging there for different reasons, like due to insufficient resources, or due to the conflicts for quota at high parallelism, or due to the startup latency when acquiring new pod at scaling up, or it spent too much time on fetching dependencies. The operator will identify such applications, proactively stopping them and resubmit them at a given backoff to avoid deadlock from happening. Let's take into example here. The CMO describes that the application requires a total of 400 executors, and it needs at least 80% of that, which is 320, in order to make actual progress. And the application would go to running with under threshold executors from submitted if the worker count it got is lower than 320. And the status will become running with partial capacity if the number of executors are tolerable between 320 and 400. And of course, running healthy means that it's got a full capacity to proceed on. If the application still cannot get minimum required executors within the given timeout of 10 minutes, the application will be shut down proactively by operator and resubmitted after the backoff of 5 minutes. User may also configure the follow-up actions for infra-level failures like this one, or app failures. Let's take a deep look into the granular state handling. The below or above threshold executors, the app or infra failures help user to identify, to predefine the follow-up actions without human intervention, like only to resubmit my application when it's failed because of infrastructure level failures. But however, it may cause a problem for the storage. Like a Spark application may switching between below or above threshold for several times due to executor preemption and restart. Therefore, as the history itself is persisted in the application, that may cause like extremely large object within the store. To resolve that, the orchestrator acknowledges the states periodically, persist them into external store for future reference, and the operator, once detected state is acknowledged, will prune that and try to keep only the most critical and most recent ones for the accuracy of state transition, as well as the human readability. The next tip we would like to share is about utilization. Actually, when you start your application, you're gonna need to specify the resources you need, including the CPU, memory, disk, for your Spark driver, and executor pods. The scheduler will identify the nodes that have sufficient resources, schedule the Spark workload on them. Setting these numbers to a super low level number may cause your Spark pods being evicted when violating the limitations. And setting them too high means the over-allocation, therefore unnecessary higher bill. It is incumbent, actually, for engineers to put an estimation over there, let it run for several times, and fine-tune the configuration based on the performance. In reality, actually, in our platform, it is possible to automatically generate the resource recommendations based on the actual run. Spark metrics includes the resource usage for all CPU, memory, disk. It has the storage of a task or a job, the add or removal of executors, the read and write size on each task. All these events could be received by hooking up additional listener to the listener bus. So in the case of managed Spark, a user could choose to opt in to analyze for resource usage. Once enrolled, the additional listener will be added to collect the metrics and send up them to the aggregation service. The metrics themselves will be analyzed by Spark with machine learning and give user the feedback and find out potential resource improvements. A resource report will be automatically generated for each enrolled application, indicating the memory, disk, CPU usage over time in the past couple of runs, and help identify the actual requirements, and provide potentially estimation on the other combination for configurations. The next we would like to discuss is about dynamic allocation. The well-beloved cost saver is now available for Spark on Kubernetes for our customers on Spark 2.4.8 and 3 and above. When you have dynamic allocation enabled, don't forget to tune your batching for executor pods, which is by default set to a pretty low number of 5. It may take just forever for your application to acquire full capacity. On Yarn, the external shuffle service helps the well-beloved cost saver to achieve this cost efficiency without worrying about losing shuffle data. It is now also possible on Kubernetes to avoid recompute of shuffle partitions with different strategies. Our Spark team at Apple also tried to contribute to community to make this available. When dynamic allocation is enabled, one needs to pick up the shuffle handling strategy. Shuffle tracking makes sure that an executor will subject to deallocation only if it is not persisting any shuffle data, or if the shuffle data persisted has exceeded given TTL. Migration-based graceful decommission helps a lot for executor or node shutdown by transmitting the shuffle data to its peer. And now with Spark 3.2 and above, you can also dynamically reuse persistent volume claims within the same application. The driver will maintain the PVCs of the lost executors and take the responsibility to attach them to the new started executor pods. And next is about history server. We're supporting a multi-tenant history server on the shared clusters. It is based on Spark 2.4 and serving actually all the active versions within the same cluster. While supporting this multi-tenant cluster, we get a feedback saying that the loading for UI could be relatively slow, especially when you have like the job running there forever for a while, and for streaming jobs, which are just assumed to be like running there forever. And in user communication, it is identified that it's not the full history, but the most recent ones are most noticeable. The user would like to answer the question like, I want to analyze the performance in the past a week, 5 days, 3 days. I want to understand why there's recent performance degradation. So that for the running jobs, our multi-tenant history server will try to aggregate and save the most recent 10K events of running applications, create a snapshot, persist them into the external blob store. When more events are received, a new snapshot will be created and persisted into the store. This is extremely helpful for answering the most recent performance of the running application. And next, data platform could run on different compute substrates. Managed Spark means an extremely easy way for users to define, to version, to deploy their Spark applications over multi-cloud. From API, from controls, source control, from notebooks, from your workflow engine. You may expect a user to ask, hey, I want to use this managed Spark with these features, but I want to run them on our existing cluster, already approved clusters, already acquired capacity. How could we achieve this one? The control plan of Spark orchestration consists of 2 parts. The unified Spark orchestrator that takes up all the API calls to maintain the same interface across multi-cloud. When a new application start request is received, it will schedule that in the target cluster and namespace. And the other part is in cluster. Spark operator takes care of the application lifecycle within the same cluster, and Spark history server ingest the Spark events and try to render them after the job is completed. Setting up new cluster for Spark control plan, therefore, could contain a bunch of trivial tasks, starting to figuring out the cluster size, the cluster version for your work case, and do maybe a bunch of Helm installation to get your control plan ready in place. And do the credential management, network entitlement management before you can really add this new cluster to your inventory and submit your application there. This process could be even more complex for bringing your own cluster, which are from different providers and may have custom customizations and for optimizations. We leverage infrastructure as code to achieve self-service style of the installation. So from a high level, based on users' situation, one could choose to provision a new cluster or reuse the old one. It's gonna need necessary entitlements for Spark, like the network entitlements to reach dependencies for metrics publishing and for log ingestion. The modern SDK, modern infrastructure as code SDKs help us to reduce the human interfere in this process. Like for example, the above resources with Plumi, it is possible to be declared within around 50 lines of code. The SDK communicates with the system being managed with desired spec. And the in-cluster control plan components, the Kubernetes resources, are also possible to be described as a code. CI/CD integration makes sure that the updates are rolled out without downtime for prod customer. Data platform, by shaping up SDKs, define the desired state for managed Spark to run on multi-cloud. Cluster owner may choose to self-install or opt-in for updates of the control plan. In practical, while designing SDKs, it's recommended to decouple Kubernetes resources, which are provider agnostic, from the other ones to improve your flexibility among different offerings for network and security. From data platform, the access for cluster and namespace is controlled at project level. A project is the logical boundary for all the resources we have. You may choose to create Spark applications, notebooks within your project, associate cluster and namespace within that. In this way, the project boundary helps us to identify only the given group of users have access to the given cluster. Spark UI, Spark history server, also does the token-based authentication to make sure that Spark UI is visible for given user only, even if the cluster itself is shared. We use federated access to make sure that the authentication story is consistent over cloud provider. As a summary, in order to scale up Spark on Kubernetes, or at least get prepared for that, one need to consider: first, get your cluster ready. configure at the storage size, as well as the compaction strategy towards write throughput, prepare for your scale. This is extremely critical for multi-tenant clusters. Explore batch schedulers. There are multiple open source solutions. The orchestration side timeout helps to mitigate possible deadlock, but the batch scheduler deals with that with fairness. Spark concurrency control policy, actually, while building that on application active index will help us to provide a better user experience than just a simple rate limiting. Spark metrics, events, and historical data could be used to avoid over-allocation or underutilization. It can be used in combination of other cost savers, including the cluster-level autoscaler, as well as app-level dynamic allocation. Modern infrastructure as code tool are your best friend to effectively add new cluster to fleet inventory. While designing that, don't forget to decouple your provider-agnostic parts as well and the other parts for better flexibility. Thanks for listening and come to us in this late afternoon session. If you're interested in our work, we're hiring. And now we're ready to take questions.
If you have a question, please raise your hand and I'll come by with the microphone.
Yeah. Thanks for the great sharing. I have two types of questions. One is about scaling. I'm curious how far you guys stretched a cluster in terms of for the wide use case. How many Spark jobs you were able to squeeze in one cluster, and did you came across any issues when the cluster is running at a high parallelism? This is one of it. And the second question is about some of the packages that you use. It seems like there are some internal packages you use, like the configuration I saw there's in the namespace. So are those features available outside or to the open sourced? Yeah, thank you.
Thank you. For the first question, the initial load test, the graph we share was like running the wide case with around 5,000 applications simultaneously start at the same time, and all of them trying to acquire, execute all the pods together, and that's like when it's trying to stuck with it. And for the next question, I would like to delegate to Aaruna for this one.
Which feature? I didn't follow the second question fully.
I think for the concurrency control one, right?
Right. The concurrency control, it's not currently open sourced. We are looking to contribute some of it back if possible.
Yep.
Yeah.
Hi. First question, which Spark operator do you use? And the second question, how did you implement the how do you implement the autoscaling? Is it the Spark operator feature, or did you implement it by yourselves? The autoscaling.
Yeah, for the first question, I think the Spark operator is what we built within Apple. It is yet open source, but we're seeking the possibilities. And for the second question, I'm not sure I fully get that.
The autoscaling is autoscaling of the clusters.
I see.
The cluster autoscaler, you mean?
Yeah. Mm-hmm.
Yeah, so we're using, it depends on the cloud provider that we're using, based on-prem or any other third-party providers that we use. So based on that, we use the corresponding autoscaler that the underlying cloud provider supports.
Thank you.
Yeah.
We'll take one more question. I was wondering for the Spark UI, how do you guys in Kubernetes world, the jobs are coming and they are going. So how after the fact you guys are able to provide Spark UI to engineers?
So essentially, we're starting up the Spark history server per cluster to process the data that should be visible after the fact of application completion.
So all the So one cluster, all the jobs from in one cluster published to one S3 and
Yep.
like that. Got it.
All right, we are out of time. So if you have additional questions, please go see our presenters. And thank you for joining us today.
Thank
and
you.
have a great evening.
Thank you.